Hi, everybody. We're Group 5, and our project is Magic the Gathering Deck Building Assistant. My name is Jarrett Mitchner.
My name is Jackson Wildman.
My name is Dakota Wood.
Here is going to be our project outline. We're going to go through the introduction first, the related work, our proposed work and results, conclusions and future work, and then a live demo.
Now we can get into some background of the project and kind of the reasoning behind why we wanted to apply data mining algorithms to this problem. If you don't know what Magic the Gathering is, it's a card game originally released in 1993. At its introduction, it saw several 60-card formats that were generally considered casual. As the game has gotten more popular, there have been more formats introduced and the game has gotten more competitive. In the early 2010s, there was a new format introduced called Commander that's led by the casual scene of the game. And it has a rule set where you have to have 100 cards in a deck. All of them have to be unique outside of basic lands. And there's a very small ban list when compared to the other 60-card formats. Because there are over 28,000 cards in the game, with very few of them being banned, deck creation can be an intimidating task for new and old players alike. And so this program aims to alleviate some of those more intimidating factors of deck building by applying data mining algorithms. So the questions that this program aims to solve are, first, whether we can group cards based on how competitive they are. Within Commander, there is a competitive scene, and there's a site called EDHREC where cards are ranked based on how often they win in tournaments, how many decks they're in, and various other factors. So we want to see if we can apply a data mining algorithm to group those cards based on that EDHREC rank and recommend them to a player based on their commander. Second, we want to see if we can draw strong or weak associations between cards based on their attributes. In this project, we primarily focused on the rules text of cards, or the oracle text, as the owners referred to it as, to see how similar a card is to a commander, draw a support score from that, and then determine whether that card should be placed in a deck with a given commander. Lastly, we want to see if we can predict the EDHREC ranking of those cards based on various attributes, but specifically that similarity score used in the associative step. So the rankings that we're predicting are based on unreleased cards. The reason that we know information about those cards is before new sets release, the owners of the game, Wizards of the Coast, will spoil cards and put out the rules text, mana cost, and all the other attributes of the card. Based on the similarity scores we achieve in the association step, we can hopefully determine the future EDHREC ranking of these cards. The next upcoming set at the time this project was assigned was Duskmourn House of Horrors, and so that is our test data set.
And now we are going to get into our related work. Magic the Gathering has been the subject of numerous computer science research projects. Previous work has focused on three main areas: building AIs to play the game, creating deck builders and draft bots, and developing game configurators. Looking at previous approaches, AI deck builders show promising results when using training models, but were primarily focused on draft formats with much smaller card pools. Knowledge-based configurators were also developed, but they had a limited flexibility in their recommendations. Our approach differs in several key ways. First, we consider the full commander card pool, which is much larger than draft formats. Instead of using complex training models, we implement data mining techniques. And most importantly, we specifically focus on the commander format, which has unique deck building requirements and challenges.
And now we're going to get into our proposed work and results.
For our initial approach to deck building, we implemented the k-means clustering algorithm to filter and group cards based on their EDHREC rank, which indicates how competitive a card is in their commander format. Our primary goal was to prioritize what we call staple cards. These are highly competitive cards like Demonic Tutor, that are valuable in many decks. The algorithm first filters cards based on the commander's color identity, since commander deck building rules require all cards to match these colors. Then it groups the remaining cards into cluster based on their competitive ranking. To measure the performance of our clustering, we looked at two key metrics: the distance between card ranks and their assigned centroids, and verification that cards were properly placed in their assigned clusters. Looking at our results, we chose to use a point distance metric instead of the traditional sum of squared errors because of how our data is distributed. As you can see in the graph, we expected and found a widespread of values across all clusters due to the nature of EDH-REC rankings. Our results show that cards properly aligned with their initial cluster assignments, which was important for our goal of prioritizing more competitive cards. While we did see some variation due to random initial selection of centroids, the algorithm successfully included key staple cards in our result, validating our approach to the clustering problem. This clustering step laid the groundwork for our association rule mining by ensuring we started with competitive card pools.
So for this project, we chose to make modifications to the base a priori algorithm. Historically, the a priori algorithm has had poor memory efficiency and time complexity performance due to the amount of rules generated and the candidate generation and pruning steps, in addition to the large number of iterations over the given data set required. And so because we want to be able to train this model live, we chose to modify the a priori algorithm by reducing the rule counts to only generate rules of size 2 for card inclusion and 3 for verification. The metric that we used for support score was similarity between the oracle text between two cards. So we wrote an algorithm to extract every phrase in each card's rule text and then compare the count of each card's rules text that match each other and take the percentage of matching terms in the target card versus the comparison card. So for the first pass of the a priori algorithm, where we generate those rules of size 2, we initially base that similarity score based off of the commander. And then as we grow our pool of cards being included in the deck, we start comparing to the maximally similar card, which has a chance to make the deck less focused on the commander, but also lends itself to including those staple cards mentioned in the k-means section. The second pass is a verification step to make sure that the cards that we drew rules with for the rules of size 2 should be in the deck. So we iterate over every card included in the deck against the maximally similar rule and compute the support for that rule of size 3 as well as the confidence. By doing this and verifying that the confidence meets a certain threshold and the support meets a certain threshold, we can verify that cards being included in the deck align with the given commander's playstyle. So some commanders will be aggressive or high damage output, and others will focus on controlling the board and protecting themselves to win in a way that might not be through just pure damage. So the performance analysis for the modified a priori algorithm shows promising results. This is a graph showing the support for rules of size 2 versus the confidence when those cards are computed for rules of size 3. We can see two linear relationships as well as some scattered cards. Those scattered cards, after reviewing the data, correspond to those staples that we mentioned earlier in the report, like Demonic Tutor and others, that let you go and search out cards and thin your deck and make it more consistent. Which is very, very valuable when making a competitive deck versus one that is purely focused on the commander. Those cards in the more linear relationships likely correspond to the commander in reference to the line showing high confidence, and then a card most similar to the commander or a rule most similar to the other cards in the deck with the lower confidence line. The rule generation step, because of the restricted size of rules being generated and the restricted number of rules being generated, allows the a priori algorithm to finish in around 10 seconds, which means that users of this program can reliably generate decks in a live setting without having to wait hours and hours for the algorithm to iterate over the entire set of cards.
So for regression, we used a linear regression model. And for this, we assumed that there's going to be a linear relationship between the EDH rank and the similarity scores that are obtained in the a priori algorithm, since theoretically, if we have a high EDH rank, we should have a high similarity score to that commander. And so the training data we'll be using in the linear regression model is 62 cards that have been obtained. Those are the ones with the highest similarity score. And we remove the commander because the commander would have a similarity score of 1. And traditionally, we've seen our values just kind of hover between 0 and 0.4. And so that would kind of skew the regression line pretty significantly, so we removed that. And so when we will use this model to predict the EDH rank of the upcoming cards, and like we previously mentioned, those will be the Duskmourn set. So here are regression results. They were not good. Our assumed idea of the similarity score being a linear relationship with the training cards and the predicted cards was not how we initially imagined they would be. So if we look at the actual versus predicted score for one in the commander, Yuriko the Tiger Shadow, we can see that the regression line is very far under. It's off by several magnitudes, essentially. And if we look at the deck, the recommended cards, and their similarity score for a scatter plot, we can see there's not really any real tangible relationship besides that most of our scores kind of land under 0.3 with a few outliers. And this is not just a one commander case. We tested this with several other commanders and we got very similar results. So our regression did not do well enough for us to really accurately predict scores. It essentially falls into random guessing territory, and the guesses are not anywhere close.
Looking at our results, we successfully answered 2 of our key research questions. First, we proved that the cards can be reliably grouped based on their EDH rec ranking, as demonstrated by our clustering results. Second, we showed that strong associations can be drawn between cards based on their attributes through our modified a priori algorithm. However, we did face challenges with our third question regarding EDH rec rank prediction. We found that the linear regression was insufficient for predicting EDH rec ranks of new cards, primarily because there isn't a linear relationship between card similarity and competitive ranking. This was an important discovery that points to the complexity of what makes a card competitively viable. Despite this challenge, our project successfully demonstrates that data mining techniques can be effectively applied to deck building processes, providing valuable assistance to players building commander decks.
So again, regarding the EDH rank of the linear model, it is a combination of various attributes. Our data set did not include the win-loss information, and the prediction of them is much more complicated. So one of the proposals we have that could possibly make this, that could predict the EDH rank better, is a regression tree instead of a regression linear model, because regression trees allow us to do a lot more of different attributes. So a lot of the attributes we have are string values or just values that aren't continuous, and that was kind of a big problem with doing regression where we can only use continuous values. And so theoretically, if we created a regression tree, we should get better predictions, and then we could even use these predictions to test with different numbers of attributes and see which ones contribute more towards the EDH rank.
So, some future work ideas for the clustering and associative steps. The first thing that we thought about whenever we were finishing up this project is that the K value for the k-means clustering algorithm is static in our implementation. It implements sort of a fixed number of staple cards, But in the future, we could implement on the front end a slider corresponding to that K value to tighten up that first cluster's value to include the most competitive cards first, rather than any similar cards. Conversely, you could relax the K value to include the most similar cards if you're playing with friends at a casual table instead of trying to compete for prizes. Similarly, in the associative step, we want to make the rule generation perform a little bit better. We did research into a few different solutions for improving the performance of the a priori step. The first one that we found was a GPU-based implementation of a priori. If we implemented this on a GPU, we would be able to perform significantly more computations over the same amount of time as if we did a single core Python program, allowing us to implement the algorithm as applied to the whole set rather than just a subset for the commander. It would also allow us to remove the restrictions on the size of rules generated. Similarly, there was a research paper done on double pruning in a priori, where after candidate generation, there are 2 pruning steps to make the candidates generated even more viable, and further reduce the amount of computations for longer rules. So as we mentioned in previous slides, in the predictive step, we would like to continue trying to predict the EDH-rec ranking, and some solutions to that would be either to use a regression tree or a classification tree, which would allow us to use non-continuous attributes like all of those text fields to expand our training data set. By doing this, we can make more accurate comparisons rather than just saying these 2 cards are similar, it should perform this way. And we can look at a more complex behavior of the card in the context of the game. So similar to the clustering improvements, we'd like to improve the interface by adding more complex card analysis explanations. We give the user more control over kind of how rules are drawn and highlight the terms in rules text that cause those rules to be drawn. We'd also like to include land-based recommendations. In our initial rule set generation, we don't include any lands, which is why we have that 62 or 63 card figure. The other 37 or 38 are assumed to be basic lands, but there are valuable dual lands and fetch lands that would give some players more options on how they want to build their deck out. We'd also like to implement a Scryfall API section for card images. Currently, whenever a card is selected, it only displays the text for all of its attributes, but Scryfall is a popular deck building site and a popular Magic the Gathering resource that allows users to pull images for card data. So we could display that rather than the text.
And now we are going to get into our live demo. So this is our Flask app. Just run that with Python. And it gives us, and it's being hosted on localhost. And so this is what our GUI looks like. And so now we can choose a commander name. So for instance, the one we did a lot of our testing with is Yuriko Tiger Shadow. And there's a little text box that appears that makes it a little bit easier to, whenever you're searching these up. So I'll select that and hit submit. And then our model will run and it'll take a moment. Okay, and now we've gotten our list of related cards and upcoming cards. So if we look at our related cards, we can click it and then we get all of its information, such as the name, the type, the color identity, the text, and then the EDH rec, as well as the EDH prediction, which the EDH prediction for a related card does not exist because it is just a related card. We're not predicting on that one. But if we look at our upcoming results, we can see that our EDH rec prediction is here. And again, it's not close, as we can see. But we can click through all of these cards, and they're listed in the highest similarity score to lowest. So essentially, for Yuriko Tiger Shadow, Ingenious Infiltrator is one of the best cards you can kind of add to the deck. And then for the upcoming results, Fear of Failed Tests is one of the best upcoming cards you can add. And that is our GUI. Thank you for coming to our presentation, and I hope you have a great day.